So in this video, we're going to be going over another application of derivatives, and this is where we're going to learn how to actually graph a certain function using the derivatives of that function. So the first thing we're going to be talking about is the first derivative test. And the first derivative test says that if f prime of x is greater than 0 for every x on some interval I, then f of x is increasing on that interval. The second statement says that if f prime of x is less than 0 for every x on some interval I, then f of x is decreasing on the interval, on that interval. The third statement says that if f prime of x is equal to 0 for every x on some interval I, then f of x is constant on that interval. So what this basically means graphically is that, so the first statement, we're just going to draw a quick visualization. So let's say this is the curve f of x, and it's saying that in order for f of x to be increasing, f prime of x, the slope of the derivative should be positive. So f prime of x is supposed to be positive. So in this case, this is an increasing function, and say if you make a tangent line right here, and we know that the derivative is the slope of the tangent line, and you see that this tangent line is a positive slope. So since the tangent line slope is positive, the function is increasing. So this is the small diagram of representing statement 1. And now for statement 2. So let's say this is the function f of x for statement 2. And this function is decreasing. So in order for f of x to be decreasing, we want to make sure f prime of x, or the slope of the tangent line, is negative. So we do something similar to what we did before. We make a little tangent line on this curve. And you see that this tangent line has a slope, negative slope, so therefore the function is decreasing. Now for the third statement, it says that if f prime of x is equal to 0, so let's say this is the function f of x. So it says that there is no so it says that f prime of x, if f prime of x is equal to 0, meaning the slope is equal to 0, every x on some interval I, the function is constant on the interval I. So let's say that this function is constant, f of x constant. We want to make sure f prime of x is equal to 0. So that means that the tangent line is basically a horizontal line, and this has a slope of 0. A horizontal line has a slope of 0, and this usually is going to refer to the critical points. When f of prime of x is equal to 0, those are considered the critical points of the function. So this is just a general overview of increasing and decreasing functions and how to just visualize them. But the actual test for first derivative is this. Suppose that x is equal to c, so there's some point c is a critical point of f of x. Then if f prime of x is positive to the left of the point c, and f prime of x is negative to the right of the point c, then x equals c is a relative maximum. So it's basically saying that say that we have like say that we have a parabola. It's basically saying actually need to make an upside down parabola. So on an upside down parabola, it's saying that if the derivative of this upside down parabola on the left side is greater than 0, meaning positive, and the derivative of this parabola is negative to the right of the to a point c, then there's going to be a maximum. So let's say we pick the point right here, this point right here. We'll label this point c, and that's just 0, 0. So the first condition says that if f prime of x is f prime of x is positive, meaning what we already determined is that if f prime of x is positive, that means that if the function is increasing. So you see on the left side, the left part of this function is actually increasing. And if we wanted to, we could actually draw the tangent line or the derivative of the function, and it would just be a straight line. This is the line of 2x, and you see that the function is actually increasing on the left side of the equation. So on the left side of the equation. So we can erase this tangent line now. So that means that on the left side of the parabola, on this parabola, the function is increasing, right? And on the right side now, you see that the function is actually decreasing. And that means that there is a maximum located at x equals c. So if it's going from increasing to decreasing, this implies that the function has a relative max. So now, if you do the same thing for the second statement, so let's do the same thing for the second statement, but let's use a different graph. Let's use a regular parabola. So you see that on the left side, this function is actually decreasing. And on the right side, this function is increasing. So that means that the derivative on the left side of the function is negative, and on the right side of the function is positive. So this function is actually going from decreasing to increasing. So when this happens, f of x has a relative minimum at x equals c, and we're gonna pick x equals c to be like 0, 0, right in the middle. So this is basically a graphical representation of the first derivative test. And for the third statement, if f of x is the same sign, it just implies that f of x is a horizontal line, and the function is going to be constant at that point x equals c. And that point x equals c is usually the critical point. So the steps to actually find these, to use the first derivative test, is first find all critical points. So it's basically where f prime of x is 0 or undefined. Then you make a little coordinate plane. Make a coordinate plane and divide that plane into subregions. Of f prime of x. So we want to determine. So what we're doing this to actually determine where f prime of x is positive or negative, since the slope directly shows us that if the function f of x, the original function, is increasing or decreasing. We want to determine where the derivative is actually positive or negative, so we can find out where the function is increasing or decreasing. So after we do that, the third step would just be to test values in each subregion. So let's actually do an example to show this. So example. So we're gonna use the function x cubed minus 12x. So first step we have to do, it says, is find all the critical points, and that's where the derivative is equal to 0. So first we found the derivative. F of x is equal to 3x squared minus 12. Now we just set this equal to 0. 3x squared minus 12. This is going to be 12 plus 12 equals to 3x squared divided by 3. You get 4 is equal to x squared, and we get plus minus 2 is equal to x. So our critical points are x is equal to -2 and x is equal to 2. So now that we found the critical points, we make a small coordinate plane to just visualize, to actually show where the function, where the derivative is actually positive or negative. So we're gonna write the critical points right here. So we're gonna label this as where the derivative is equal to 0. Those are the critical points. And now we just pick values. We just pick values in between the subregions. So from negative infinity, so this right here is negative infinity, this is positive infinity. So in between negative infinity and -2, we can just pick a simple value like negative, let's say -5. And in between -2 and 2, we can just pick simple values like 0. And from 2 to infinity, we can just pick a simple value such as 5. And when you evaluate these, evaluate each of these points at with the derivative. So let's evaluate them. So f prime of -5 is 3 -5 squared minus 12. 25 times 3 is 75 minus 12 and 63. So in between a negative infinity and negative 2, the derivative of f of x is positive. Now for f prime of 0, 3 0 squared minus 12, and we get negative 12. So in between negative 2 and 2, the derivative is negative. Now f prime of 5 and in between 2 and infinity, the derivative is also positive. So now that we've determined we determined the signs of the derivative in each subregion, now we can determine where the function is actually increasing or decreasing. So in between negative infinity and negative 2, the function is increasing. So let's use a different color. Increasing. In between negative 2 and 2, the function is decreasing. And in between 2 and infinity, the function is increasing. So using the first derivative test, the statements we had before, it says that if the derivative is positive to the left of the critical point, and the derivative is negative to the right of the critical point, then then that critical point is a relative maximum. So do you see that? You see over here with negative infinity and negative in the interval negative infinity and negative 2, on the right side, on the right side of this critical point, so negative 2 is the critical point and 2 are the critical point, but right now we're going to focus on negative 2. So to the right side, to the left side of this critical point, the function is actually increasing, but on the right side, the function is actually decreasing. So at x equals negative 2, there is a relative maximum. There's a relative maximum. Now we do the same thing with the other critical point, and you see that for this critical point, on the left side of this critical point, the function is actually decreasing. It's decreasing because the derivative is negative. And on the right side, the function is increasing, and that's because the derivative is positive on the right side. So we can say, because we know that now, we can say that at x is equal to 2, there is a relative minimum.